Okay, so today we're going through electrostatics, which is quite an important topic because it's always going to have one or two questions at least being tested. Uh, I will the easy as usual the easier parts I'll just skim through it and then I'll talk more about important stuff. Okay, so it's very similar to gravitation in that all the equations are almost basically the same. You just replace anything that has mass with charge, and the constant in front instead of g you use k. Uh, I think for these equations, you guys should already be quite familiar with it. And more importantly is, I think these, uh, just like gravitation, electric field is a conservative force. Electric force is a conservative force. So there's a potential associated with it. And then usually by determining the potential, you can determine the force lah. So it's quite useful. Uh, and then electrostatic questions will always boil down to a few things. Like if you are thinking like in the exam, you don't really know what to do, right? When you get a question, you don't really know what to do. You can just ask yourself like, what could it possibly test? First is continuous charge distribution. That's the first possible one it could test. Then second is like Gauss law. And then third is like superposition. Okay? So most of the time, it will test one of these three lah. And then maybe I think possibly could be other stuff, but it's one of these three usually. So either you brute force, you use Gauss law, or you use superposition, or you can use energy. Um, for the brute force one, is literally just integrating. Usually you will always write, you'll start by writing something like this. So you'll find an expression for dq. If you are given linear charge density, like for example over here, then you will write dq equals lambda dx. If you are given area charge density, then you'll write dq is equals to area charge density dA or ds. And then if it's volume charge density, you'll use rho dV. Okay, so usually you'll write it in these forms first, and then you integrate over all the charges to determine the electric field at a point. So in this case, we are determining the electric field due to an infinite wire. Um, Wait, not infinite wire, a wire of length 2L. So you can just integrate from negative L to L. Okay, and then the other thing that is important for this kind of question is that you must remember, usually, right, due to symmetry, the electric field will end up pointing in one direction. For example, over here, I think it's quite obvious that the electric field will be over here or the other way. But in this case, it's positive, right? So it'll be pointing away. And then you just remember to take the component in that direction. So you need to take this component, not the full kq over r squared. That one is like the full component. You need to take uh, part of it, basically. So in this case, the component is this term over here. So this is the one that you need to take care. Make sure you don't forget adding this extra factor to account for like what you're looking for. Okay. And then there's also this thing called building up layers, which has been tested before. That's why we added it in. Uh, Basically, the idea is that you can perform a step-by-step analysis to solve problems. So, for example, if the problem asks for electric potential energy of a charge district of a sphere, then you can imagine assembling layers and layers of spheres, like concentric layers of spheres, one after the other. And then you can use the shell theorem to determine the electric field at the boundary of each one, which is just kq over r squared. And then you can just write it as infinitesimal amounts of energy you need to add and integrate over all to determine what the total amount of energy you will need is. So the learning point from this kind of question is like you can use a step-by-step approach. So you slowly add on one by one each charge element. And then electric dipoles, for the purpose of SPhO, I think dipoles are not that commonly tested. Even like last year, they tested magnetic dipole, but you just really needed to know how to apply the formulas. So the two formulas that you need to know are this one, P equals QD, where P is the dipole moment and D is the distance between the two like charges. And then the other one you need to know, the other pair you need to know is the torque and the energy one. Then the equivalent for magnetism is like M cross B. and m dot b. Wait, sorry. Okay, so just I think for this one you don't need to overthink it. More importantly, you just need to know the formulas because for SPhO they care more about breadth over depth. But if you want to prove like there's an equation for the dipole field, which you can prove by simply assuming it's 2-point charges. Yeah. Um, okay, you can just Google lah. I'm a bit lazy to write out the full equation. I think you're not expected to know it either. Uh, okay, I'll spend more time about this one on this one because Gauss law is very, very important. Guarantee you about 90% of problems will probably ask something to do with Gauss law. So the idea is that uh, if you draw a Gaussian surface, so Gaussian surface can be anything actually. It doesn't have to be a sphere, cylinder, or a box. It can really be anything as long as you draw a random surface, but note that it must be closed surface, so it's not open. Then if you sum up all the electric flux through this surface, it must be equal to the charge enclosed divided by a constant. So flux, if you guys remember, is E dot dA. So it's like if the field is, so dA points in a direction normal to the surface. And then if the field is like here, you need to take the dot product. And then if you sum up the dot product across the whole surface, it must be equivalent to the charge enclosed inside divided by a constant. Um, Over here, we put the integral symbol, which basically means summing up all the flux. But in a lot of cases, especially for SPhO, right, you don't have to do any integration, or maybe it's minimal integration, because symmetry allows you to uh, simplify the problem. So what do I mean by that? If we look at the sphere case, right, we want to determine the electric field inside a sphere. So in this case, we choose a Gaussian we choose a sphere to be our Gaussian surface. The reason is because for a sphere, right, if we're determining the electric field inside, it has to point radially outwards at any point. So the reason why this is so is because if you imagine rotating the sphere in about any axis, right? If the component was not purely radial, then the electric field direction would change, but the charge configuration is still exactly the same upon rotation. That's what we mean by symmetry. So it cannot have a non-radial component, if you guys know what I'm trying to say. Like if it had a component like this, right, then you rotate it, then this component will be pointing in a different direction. But the charge distribution is still the exact same after rotation. So how can that be? That means that the only component must be radial. And then because of this symmetry, it gives us a simplifying assumption, and then it allows us to reduce integral into just like an algebraic expression, which is the electric field times the area of a sphere. Okay, so note here that the small r is defined like this, and then r is the total radius. Okay, so this is the area of our Gaussian surface, the electric field, and then we equate it to the charge enclosed. So the charge enclosed, we are given the charge density, so we multiply it by the volume. This is simply the volume of the volume bounded by our Gaussian surface. And then you just do a bit of math and you get this. And most notably, right, just like gravitation, the field inside a charged sphere is directly proportional to r. So the field against distance graph looks something like this. So it'll go up to some point and then it'll fall off according to 1 over r squared, where this is r. Okay, so initially it's linear, then it falls off. And then also note that it's smoothly joins at r equals r. So it's a continuous function. Okay, so we can apply the same procedure of symmetry, then apply Gauss law for cylinders. So if you imagine a wire. Oh, also, if I'm going too fast, you guys can tell me. I assume you guys have heard of this stuff at least already. So there's linear charge density lambda, and we want to find the electric field at distance x. So once again, right, by the same logic, the electric field has to point like outwards, in radially outwards, because of the same argument we presented earlier. If you rotate it, the charge configuration stays the same. So it can't have any like tangential component. And because of that, right, we choose a concentric Gaussian cylinder to be our surface. And we can construct this cylinder around our original wire. So okay, and then we let this cylinder have some length x. So all the field is going perpendicularly against the surface. And that is why the integral, we don't have to deal with the integral directly because each component is already perpendicular to the surface. Um, this is just the area, the curved surface area, and then this is the charge enclosed. Okay, so the length here is L. And then you see that the L and L cancel, so it's not dependent on L, and it gives us the final function like this for the electric field, okay, which is 1 over x, which is proportional to 1 over x. And then the same routine applies for an infinite plane of charge with surface charge sigma. If you draw a box, so if you imagine a box that extends above and below the surface, then you would know by symmetry, or you can kind of common sense by symmetry, whatever, that the field will be going up and down, right? So once again, the integral is trivial. You can just write 2a, where a is the area, the area of the face of the box, is equals to sigma times a over epsilon naught. Okay, and then the a's will cancel out, and you will yield the final function for e. And most interestingly, right, this function isn't dependent on the distance from the plane. So it doesn't matter whether you're here or here, like the field you experience is the same. Intuitively, I think in Griffiths, he says something like, you can imagine it's because when you're higher, you can see more like charge or something like that. I don't know, lah. I guess you can convince yourself about that. Do you guys have any questions up to this point? Like, am I going too fast, or is it okay? Okay, if everything is fine, then I move on. Okay, so the next thing is there's this thing called charge boundary. So in general, right, when you have free space, so when there's nothing in space, electric fields are continuous, which means that the function cannot have a sudden jump. It must be a smooth function for the electric field, right? But this won't be true if your boundary is charged or if you cross a charged boundary. So if you imagine, right, let's think about um, let's think about the example right before this, which is the infinite surface one. When we drew our Gaussian box, the field above and below are discontinuous due to the charge contained within the box. So if you imagine, right, let's say that due to some external charge, so let me draw my box first. Let's say that there was some external charge here or something, some random charge configuration that resulted in some external field like this. External field E naught, okay? By our Gauss's law, we should have, like, the charge on the surface itself will produce E up, will produce E upwards and downwards, and E downwards, okay, when you go across the plate. And because electric fields obey the principle of superposition, this means that the net effect is that on top it'll be E naught minus E, and then at the bottom it'll be E naught plus E. So it's discontinuous across the surface. There is a sudden jump of 2E, okay, which is what this thing is trying to say over here. This is just 2 times of this. So there is a jump across the surface because of the charge contained within the boundary. Okay, so that is the idea. A charge boundary also gives rise to something called electrostatic pressure, which is basically the force one specific charge element feels due to the field of everything else. Okay, so there is an easy proof for this. And the way you understand it is, okay, I'll use the example of a sphere, okay? What is the electrostatic pressure of a sphere? So if we imagine the surface of the sphere, right? Let's draw a very, very small box. So very small as in the order of like infinitesimal quantities. Because it's very, very small, you can approximate the surface to be roughly flat, to be an infinite plane of sorts. So if it's infinite plane, right, and you draw your Gaussian, you can basically apply this like Gaussian box idea again if you are dealing with a very, very, very small area. Because from your perspective, it'll basically look like an infinite plane. And then because of that, right, the argument here is that um, you use your Gauss law and then you will determine that there should be a field up and down by E, okay, due to the charge contained. But then the problem arises because in reality, right, we know that for a sphere, due to the shell theorem, the field inside is zero. And then the field outside might be, I'll use E prime. Okay? So this means, so the question is, what is the E field due to the rest of the charges at the location of this charge element? We know that due to this charge element, there's a field E upwards and a field E downwards, but in reality, it becomes zero inside and E prime outside. Therefore, the only explanation, so let's call the field due to the other charges E other plus E must equals to E prime. And E prime is equals to E. Wait, sorry, E is equals to E other. Okay, does this make sense? So basically, below the surface, it will cancel out, which will give you the reality of the field being zero inside. And then when they add together outside, it will give you the actual field, if that makes sense. And how does that yield this? It basically says that you can just take, so if you guys know, pressure is force over area, right? Oh, my handwriting is terrible. Pressure is force over area. So if our force is sigma A dq, wait, sorry. If our force is dq times E over A, and dq is sigma times A, and the A will just cancel, okay? So we are left with sigma E, which is just sigma times this thing. Wait, sorry, sigma times this thing, right? Because the question is, what is the pressure that this thing feels due to the rest of the charges? So we've proven that E equals E other. So E other is sigma over 2 E naught. And therefore, you can just multiply sigma squared to get the pressure by this logic. Okay, does this make sense? Okay, if it's fine, then the other thing is, this one you can just memorize this equation. The other way to find electric energy is you can integrate the electric field by doing this integral. I have very rarely encountered this method, but we put a problem in the questions below, so you can use it. But I think it's not that important because it's much less common. Whereas this electrostatic pressure thing has been tested in SPhO before, so I think it's more important to understand this one. Okay, so this one you can just memorize now. Okay, then the next one is this conductor thing. So conductors are materials where they conduct, as the name implies, they conduct electricity. So it means that charge can redistribute itself. More importantly, these are like what the learning points are. You need to be very familiar with these. There are a few properties conductors obey, which is that inside a conductor, the net electric field is zero. The reason this is true is because if it is not zero, then it wouldn't be electrostatic anymore. Like electrostatic by definition means no moving charges. If the electric field is non-zero inside a conductor, charges can still move. Okay? Um, Second, charge density rho equals zero is inside. This is because charge will reside only on the surface. Okay? And then third is the E field must be normal to the surface. So even if you have a non like normal surface, like if you have a weird shape, the field at every point must be normal to the surface. Okay? And then it gets destroyed because of the surface charge, the discontinuity we just talked about. And then lastly, the conductor surface is equipotential. So this is simply because inside the conductor, the field is zero. So I can get from point A of the conductor to point B without encountering any electric field. And if I don't encounter any electric field, there's no change in potential because recall, change in potential is like integral E dl, right? So if my field is zero everywhere, then my change in potential will be zero everywhere lah. So I think that among these four, most importantly, 1 and 4 are most important. These two are very important. Okay, 2 and 3 are less important now. I have rarely seen questions that would require you to invoke this. Okay, there is this thing called grounding, but actually before we talk about grounding, right, I want to talk about, it's not really in the notes, so it's important, but it's still very important. There is this thing called electrostatic shielding. Do you guys know what that is? Okay, it's like if you have a sphere, right, then it has a cavity. The point is that if you have any external charge distribution, the field inside this cavity will be zero, regardless of like what the charge outside is. So in essence, the cavity is shielded from the surrounding, which is why like when there's lightning, they tell you not to. They tell you like it's safe to hide inside a car because a car generally is conductive. Then it will shield you. So let me explain why it will shield. Oh, also similarly, right? If you put any charge inside, not similarly, but more interestingly, if you put some charge inside, it will convey the information outside, and the field outside will actually act same as a point charge. Um, Let me explain why. Okay, so I'll start with this case first where the charge is inside. So let's say, right, you place a charge not necessarily at the center. By our first property, um, the electric field inside the conductor must be zero. So what actually happens is that this plus charge will attract negative charges on the inside, maybe more dense over here and less dense outside. And it will attract an amount of charge that exactly cancels out negative Q. Um, this is because if you then draw a Gaussian surface around it, then because the Q is zero, the field must be zero as well, which obeys your first principle. And then because the charge kills itself within this Gaussian surface, the remaining charge, if the sphere was neutral, will redistribute itself evenly. Okay? Outside. So there'll be plus Q exactly outside. And then these two cancel each other out. So then it will just basically be a sphere of charge, which if you know from shell theorem, outside it will just be 1 over kq over r squared already as usual. So Actually, right, this does not apply for the case where the cavity, I mean, this does not just apply for the case where the cavity is a sphere. In general, the cavity can be any shape. It doesn't really matter. It can be some weird shape. If you put a charge, it will attract an amount of charge that is exactly equal to it to cancel it out, and then the remaining charges will distribute themselves evenly. I think the important word here is evenly. And if you're wondering why it's even, I mean, you can just kind of think it as these guys cancel each other already, so there's no force acting on the charge that will make them move preferentially in one direction. So they kind of just spread themselves out. Alternatively, you can also use uniqueness theorem, but I think that's not very important. Okay, so this is the electrostatic shielding case for putting a charge inside. The other case is if there's lightning outside, right, or like some electric field, then we want to prove that the field inside the cavity is zero. So let's say that there was a charge over here plus Q. So if there is plus Q outside, right, what will actually happen is negative charges will be attracted to the surface, some more than others, and then the field inside will be zero. Then there's a reason why lah. Wait, hang on, the plus charges should be repelled. The reason is the proof is quite simple. If you draw a like any arbitrary line going from like point A to point B, um, it tells us that delta V should be the potential difference should be integrate the field dot the path. But we know from um, property number 4, all points on the conductor must be equipotential by definition. So between point A and point B, there's no potential difference. And it doesn't matter what path you take. It can be like this also. Oh, it can be like this also. Like the potential difference is still zero, which means that therefore, because any path will yield zero, the electric field must be zero inside lah. And then um, you can also check that this satisfies boundary conditions. So, which is that like the field being zero inside won't affect E being zero in the conductor. Yeah. Do you guys have any questions about this? Okay. Um, 2.14 is a very good question applying properties of conductors. I'll go through it later because it puts into practice like all these conditions that we just talked about. Um, the example is quite straightforward, so I don't think I'll go through it. The other thing is there's this thing called method of images. Uh, I think the most general case you guys are already familiar, right? Like if it's an infinite plane that's grounded, you can just put a charge below. So if you're wondering why this holds, it's because of something called uniqueness theorem. So uniqueness theorem basically says that if there is one solution that will satisfy your boundary conditions, then it must be the only solution. The boundary conditions here refer to these four. So if you can find one solution that satisfies these four conditions, it means that it's the correct one now. And we can check that putting a negative image charge for an infinite plane does indeed satisfy all the four conditions. For example, the field line will be like this. My drawing is not very good, but the field lines will all be perpendicular to the surface. And then if you check, the potential will be zero along the surface because it's grounded. So any point over here, let's say it's kq over r, will be cancelled out by a symmetric negative kq over r. So the potential is zero. Okay. One thing about method of images is that you need to be careful what is your kind of fake region and what is your real region. You need to be sure that you're not calculating anything in the fake region. So what do I mean by this? When you apply method of images, right, you are only allowed, it's only legal to calculate fields in this region. In the bottom region, right, you cannot calculate any field. So you cannot say the field here is actually the sum of these two. That's not allowed. One, you can check that that's like false because of the properties of conductor. Two, that's just not allowed because of the way method of images work. It's kind of like guessing a solution. It's not a real thing. The charge doesn't actually exist there. Okay, so in the next example, when you apply method of images for sphere, right, you cannot calculate stuff in the sphere. So if you put a plus q over here, then an image charge forms over here. You cannot calculate the field in the sphere because this is within your image region. You can only calculate the field anywhere else. Okay. And then the other thing is that energy does not operate as simply because once again, this is not a real charge. Image charge is not a real charge. You cannot simply do your kqq over r thing. You actually need to imagine moving the charge from infinity all the way down. Yeah, so you need to integrate as if you were moving the charge from infinity to the specific point to yield an answer that is actually different by a factor of 2. Okay, so moral of the story is it's not a real charge. So be careful what you're doing. If you're applying a formula that assumes a real charge, it's probably wrong. You need to start from first principles. Okay, that's the moral of the story. Um, so besides a plane, right? The other case you need to be familiar where you can use method of images is sphere. So there is a reason why sphere allows method of images. I think it has something to do with Euclidean geometry, but I'm not too sure. So I think it's not important. But what you do need to know is like these equations, or at least how to derive them. I don't think it's that hard to derive. It's more of tedious. Basically, you just assert that the potential across this surface must be zero, where you define like a random point r, and then like you set the potential to be zero. Then you can derive these relations already. But I think if you want to save time, you can just memorize it lah. So these set of image charges basically allow you to put the surface of the sphere to be v equals 0. Okay? So let me reiterate. This pair of image charges q and q prime allow you to give v equals 0 on the surface. It does not mean v equals 0 does not mean q is equal to 0. Okay? Just because something is grounded, just because something is grounded doesn't mean the charge is 0. The charge is whatever it needs to be to yield potential to be 0. You can use the image charge to find force, that's fine. Just not energy. Okay, and the other idea is this Gauss law. This is more advanced, so I don't think it'll come out in SPhO nowadays, but it's not that hard. And also it's very useful in the future if you guys go further. So we use an SPhO problem that's modified for illustration purposes. The first part is just integrating. They want you to find field due to a ring, so I won't go through that. So the second one is they're asking you to find field within the ring. So initially, right, you're just finding field like along the axis of the ring. So to find the field along the axis of the ring is trivial. you can simply integrate because it's an easy integral. But if you want to find the field like over here, right, it's much more difficult, right? Because now you break symmetry. Like if you go off center, then each charge will no longer be at an equal distance from the point. So it's not that simple anymore to just integrate. There are two different ways to approach this problem generally. First is you can still try to brute force using cosine rule. What you do is you use energy approach. So you define the displacement to be x, and then you like sum up, you integrate over all using cosine rule, then you get u as a function of x, the potential as a function of x. And then you perform a derivative to determine the force. Determine the field. This is tedious and very prone to careless mistakes, even though it does work. So the idea is that you can use Gauss' law. What we do is we construct a Gaussian surface. More importantly, I want to emphasize that this is a like infinitely small, infinitesimal, I guess, Gaussian surface. So it's a very, very small Gaussian surface with dimensions r and 2z. The reason why I want to emphasize small is because we're going to use some assumptions here. The assumptions being that we can just assume the field is constant across this surface to first order, okay? To first order, because you are multiplying a small change in field by a small area. So to first order, you can just neglect. You can just assume the field is constant across the surface. So once again, right, we have these fancy integrals, but do not worry. If we are working in the first order approximation, we can just assume the field pointing up is constant throughout the top surface, the top and bottom surface. So by Gauss's law, right, if there is no charge enclosed in this cylinder, then it means that the flux, the net flux entering the cylinder must be zero because there is no charge enclosed. So we can simply sum up all the flux and assert it to be zero. The flux through the top and the bottom surfaces are leaving because of the reason we have proven, because of part one, basically. We get this expression for E. So we plug it in and multiply by pi r squared. This is the flux through the top and bottom surfaces. Okay? Once again, they are to first order, so we're assuming it's approximately constant. Then we want to determine the field through the sides, right? Because the question is asking for what the radial field is. You can simply take it E multiplied by the curved surface area. Because once again, to first order small, we're assuming it doesn't change. Thus, the electric field will be this because you equate these two. The flux in must be the flux out because the charge enclosed is zero. And this allows us to find the radial electric field without integrating anything at all. We purely used symmetry and Gauss's law once again, okay? So, moral of the story is that for a lot of problems in physics on field, right, even though Gauss's law explicitly has an integral symbol, you don't actually need to integrate. You can use a lot of simplifying assumptions, being symmetry or this kind of assumptions to get our answer. Okay? So this specific idea of drawing a very small Gaussian surface is useful when you know the electric field along one axis and you want to find the electric field along an orthogonal axis, along a perpendicular axis. Okay? So in this case, we know the electric field along this axis. We want to find the electric field along these axes, which are like perpendicular. So this trick will work well in these situations. Okay? Do you guys have any questions? Okay, if don't have, then we'll go through the problems. Um, I have quite a lot of requests, so today we'll spend more time on problems. Uh, okay, so the first one I'll go through is 2.6. Okay, so for 2.6, right, at first glance, it might look like just matter of images until you notice that the setup is slightly different. Instead of a grounded sphere, you actually have a conducting and insulated sphere. So insulated from the surroundings. Um, if you want to determine the potential of this, on the surface of the sphere, you still need to use image charges, but with a bit of a modification. So this question emphasizes the importance of uniqueness theorem. Once again, method of images is just a tool to guess the correct charge, to guess a charge configuration that satisfies the boundary conditions. Like, just because it isn't grounded doesn't mean method of images won't work. As long as you can guess a combination of image charges that will satisfy all the conditions you want, you can still use it, okay? So what do I mean by that? In this case, our sphere is not grounded, which means that it has some finite potential, V. When we place like our sphere, our charge, I mean, at a distance, from the sphere, we will, if you use regular method of images, you will have like a E prime over here. Or maybe I'll use Q. I'll use Q1. And this, remember that this will yield V equals 0 on the surface. But we know that V is non-zero because it's not grounded. So the trick actually for this question is that you can place a second image charge at the center of the sphere. Okay? So if you're wondering why this works, right? The first image charge enforces the condition that V is 0 at the surface. Okay? The second image charge is equidistant from every other point on the sphere, which means that it will raise the potential of the surface by a uniform amount. And that satisfies the condition that the surface of the conductor must be equipotential, right? I think that was the fourth condition in the notes. Which means that this charge configuration will yield the correct answer. Does that make sense? If that's okay, then we can use the second condition, which is that the net charge on the sphere is 0 because it's electrically neutral. Which means that Q2 is equals to negative of Q1 because the image charges within the image area still represent the total charge in the conductor. Okay? And then we can simply use the results previously. So I'm just going to quote the results, but if you guys want to refer, you can look at the derivation over here. So I'm just going to quote these results. This length, so from the results, Q1 is negative E A over R. And then by this result, Q2 must be just positive of whatever this is. So the potential at, oh, wait, sorry, this length, I'll call this length B. This is equals to A squared over R from the result previously derived. And so we can then determine the potential at the sphere due to these three image charges. So we know that these two will cancel out, right? So like, really, we only need to care about this one. So the answer is just V at the surface is 1 over 4 pi. OK, which is E. It's just like this. Right? Um, the person. Wait. Because the first image charge already yields V equals 0 with the second one. So we only need to care about the second image charge, Q2. Okay, can. Nice. Okay, so part B, determine the resultant force. So the force now has two contributions, which is the first image charge and the second image charge. Um, the charge due to the force due to charge two is just 1 over 4 pi. It's just like this. So I won't simplify that. And then the force due to the first image charge is 1 over 4 pi epsilon naught. Right? And you just sum up these two to get your total force, and you should get some autistic expression, which is a bit long. Uh, okay, you should get this after a lot of simplifying. Okay? The math is not important, the understanding is more important. The idea is just you need two image charge. And also, right, it also means that for like any general conductor question, you can kind of play around with putting in image charges. You don't necessarily have to do something textbook. You can do something weird by finding a configuration that allows you to satisfy the conditions. Okay? Most of the time, you just need to check E equals 0 in the conductor and V is constant across the conductor. You only need to really check those two conditions lah. The rest are like not that important to check. Okay. Um, the next question request I had was 2.7. Okay, so 2.7 is a very good one. Actually, I should have placed it lower because it's quite difficult. Did any of you do it? I know I couldn't do it last time. Okay, so there are two ways to do this problem. I will introduce both. Actually, I'll just briefly mention the first one. Okay, the first one, it appears as an example in Griffiths. It basically says that before you consider, okay, so first the setup is a ring and a sphere. Okay, this one has radius r1, this one has radius r2, and then this one has charge q, this one has small q, but q is equal to 0. So the way that like the book does it is you first, instead of considering a ring as a whole first, let's just consider what happens if it's just a point charge. If there was just a point charge and you try to average the potential, like the averaging will be much simpler, correct? Because your integral would be much more trivial. you can average the potential by simply doing like potential times an area element. So you do V. So if you have like a point R, so let's say this is R. If you have random point R, the potential is just um, KQ over R. And then you can do it dA, where dA is the area element. You integrate over all, and then you divide by the total area, 4 pi R2 squared. Okay, so you can use this approach to average. If you do this math, you will actually see that the potential, the average potential on the surface of the sphere is the exact same as the potential at the center of the sphere. So the result will be KQ over Z, where Z is the distance between the two. Okay? If you want to check your math, you can look at the book. It's under chapter 3. It will reduce to this expression. So the learning point is that the average potential on a sphere due to an external charge is the same as if you are just calculating the potential at the center of the sphere. Okay? And then after you come to that realization, the problem becomes trivial because every point is equidistant from the center of the sphere on the ring. Okay? So you can simply sum up all the components, model this as many dqs, and then you just sum up. Each dq increases the average potential by some amount k dq over z, where z is like you need to use Pythagoras theorem. Okay, so this is the first method. You still need to do a bit of integration, and I think it's generally quite hard to think about this. Okay, both methods are very hard to think about by yourself. But I think this is the more orthodox one. The second method is like very interesting, and I don't think normal people would think about it. And the idea actually is to use electric potential energy. Okay, so let me illustrate. In general, right, let's say Q was non-zero. Okay, so we have some arbitrary charge on this sphere. The potential energy of the system has three contributions. First is the potential of the ring due to itself. So the collection of charges in the ring will generate some potential energy, sorry. And then there is also the sphere itself, if the sphere has some finite charge. And then lastly, there is U, ring, and sphere. So the interaction between the charges on the ring and the charges on the sphere. There are three total contributions to the total potential energy. Agree? Once you realize this is always true, let's think about the difference between this case where Q is non-zero versus Q equals 0. We're trying to find average electric potential. Average electric potential is due to the ring. It will not change whether or not there is Q, as long as we are considering the ring-sphere interaction. Okay? So the average potential on the sphere is not affected by whether or not Q changes, if we are considering the third interaction. The reason is because the third interaction tells us Q times U bar is equals to big Q times V. So in this case, Q is the charge on the sphere, and V is the potential at the ring due to sphere. Okay, so this is at the ring due to the sphere. So this is kind of like Newton's third law. You can either think about the potential due to ring on the sphere and then you multiply it by all the charges on the sphere, or you can do it the other way around. Potential at the ring due to the sphere multiplied by the charges on the ring. It's kind of like Newton's third law. It's the same. And this equation both represents the third interaction. Okay? And we realize that U prime does not change whether or not Q exists. Even if Q doesn't exist, the potential due to the ring charges are still going to be the same. So then, the next thing we can do is we can find V. V is simply Q over 4 pi epsilon naught root L square plus R1 square, right? Because it's just a constant distance z from the center of the sphere. And by shell theorem, the potential outside of a sphere is just as if it was at the center. Okay, so z is root L square plus R1 squared. Okay, so I have a question. The question is, can you explain why QU bar is equals to QV? So the ring sphere interaction, so okay, there are charges on the ring, so let's call this Q, and there are charges in the sphere. Okay, wait, I'll use a different color. This one is small q. So they interact between themselves, right? There is some finite potential energy due to itself, so I'll call that U ring. And then the small q ones, the one in the sphere, also interact with themselves, so there's U sphere. But then due to each other, in each other's presence, there will be an extra energy term, which is the interaction between these two, U ring sphere. Okay? We are looking at the third one, this interaction between the two right now. The point is to realize that you can write this in two different ways. You can think about it as Q1 on Q2 or Q2 on Q1. So big Q on small q or small q on big Q. Just like how if you just had two charges Q1 and Q2, you can write the potential energy as K Q1 Q2 over R, or you can write it as K Q2 Q1 over R. Like it doesn't really matter. Recall that KQ1 over R, this is the electric field, as this is the electric potential, you multiply by 2. So this is potential due to 1 multiplied by Q. Or you can write it as potential due to 2 multiplied by 1. Wait, this is not a fraction. And do you see what I mean? You can either write it as this is V1, or you can write this as V2. It does not matter. Like it's Newton's third law, right? Like both forms are equivalent. Yeah, so big Q and V. So this thing is like saying potential due to sphere on the ring. Whereas QU bar is like potential on sphere. Wait, sorry, potential due to ring on sphere. Due to ring on sphere. Okay, does that make sense? It's kind of like Newton's third law, right? Like force of A on B is force of B on A. Potential of A on B is also potential of B. Okay, not like the energy is equivalent now, right? And they are exactly the same, like by the same logic. Mm-hmm. So, okay, now that you've understood this, okay, yeah, then you'll see that actually the small q cancels out. Because q times u bar is q times v. So q times u bar is q times q, 4 pi, blah, 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 blah. And then the q and the q will cancel. So you will get the final function for u bar, which is just kq over r1 squared plus l squared. Okay? So yes, I do agree that this is very hard to think about by yourself. I cannot think about it myself also last year. Um, but I think that it's just quite cool, this idea. And the Newton's third law idea applies. Sometimes it's easier to find force of A on B than it is B on A. Um, I will illustrate this point in another problem. Is everyone clear with this problem? So it's quite ingenious, the solution. Okay, I will assume that you guys are all okay with it. Then the next one, let me see. Okay, the next one is 2.11. Yeah, so this is the one that I was going to talk about next. Okay, so after this, maybe y'all can have a break. Um, there's a square, and there's a charge. So most importantly, this is A over 2, and this is also A over 2. And as the hint suggests, this is because the charge is right in the middle of a cube. So if you imagine a full cube, it's right in the center lah, basically. Okay? And this is useful because we can use the idea of flux. Okay? So recall flux is E dot dA. So in this case, right, we want to find the force exerted by the square on the charge, but this is also equivalent by Newton's third law to um, force exerted on square by charge on square. Okay, so it might be easier to find out what the electric field is due to the charge since it's just a point charge. And then what we realize is that at every point on the surface, right, it does not have to be below the charge. If the field was like this, we only care about this component, right? The component normal to the face. Because of symmetry, we know that the force must act along this line. So it means that we only care about the component normal to the surface. And if you only care about the normal component to the surface, you are basically doing a dot product, right? That's what a dot product is. You're finding component of A projected onto B. So this is B. Wait, sorry. If you want like a unit vector, the component is just A dot B, right? Um, yeah, so actually, right, the problem is equivalent to finding the flux through a face. And the special value of A means that the charge is right in the middle of a cube. If it's right in the middle of the cube, then by symmetry again, the flux through one face is just the total flux divided by 6, because there's 6 faces. So the flux through one face is equals to Q over epsilon naught divided by 6, right? Because there's 6 faces. Okay, so now we write what the force is. The force is equals to integral E times sigma dq. E times dq. But dq is equals to sigma dA. Alright, and then we establish that E dA is just the flux. Okay? So actually the answer is just Q times charge over 6 epsilon naught. Can? Okay. Um, you guys can have a 5-minute break, and then we'll go through. Let me see. 2.14, 2.15. Okay, after the break, we'll go through 2.14, 2.15, and then also I have a request for. Oh, okay, just 2.14, 2.15. Okay, be back by 5:13. Are you guys back? Okay, we'll go through 2.14 first, since I got a request for that. It's a very good exercise on conductors, so very worth doing. If you're wondering where it's from Russian Physics Olympiad. Okay, so the idea is that, okay, so when I first did this question, I tried to use method of images. I don't know if that's what you guys also try to do. Did any of you try that? But if you did, you probably would have realized that it's a bit messed up because you'll be trying to find potentials in the area where you cannot find potential, like the illegal area. Um, so the other thing I would suggest is you just use um, properties of conductors as usual. So for part A, what you can do is you use the electrostatic shielding thingy. Okay, so let's think about firstly, right? When the switch is open, what happens when the first charge is placed? Okay, so if you just put Q1, um, there will be like some negative charge induced on the inner surface, correct? There'll be like outer surface and inner surface, even though it's a thin shell, but there will still be an outer and inner surface. The inner surface will contain negative Q1 in order to electrostatically shield it, right? That's our first boundary condition. And then on the outer surface, we established that there'll be plus Q1 due to the discussion earlier. When you add the second, when you add the second charge, Q2, uh, it does not really like affect the potential at the center because it once again it's shielded from the outside, right? Um, does that make sense? So actually, what you end up having is that the potential at the center is just uh, KQ1 over R. Wait, sorry. Yeah, so you need to add up the potential due to this, and this. And then these two will just cancel out, right? Because they're both like, even though the charge distribution need not be uniform. So earlier, right, we said that if just Q1 was present, the plus Q1 on the outer surface of the thing will distribute itself evenly in order, because there is no other, like, there's no orientation the charges would preferentially go. But in this case, you have a Q2. So Q1 need not be even. You could have more plus charges over here. Wait, sorry, you could have more plus charges over here because they're being repelled, and less over here, right? The thing is, they are still all at a common distance away from the center. It does not really affect it. So they are still at a common distance of r from the center. So this effect will cancel each other out. So really, you just need to find the potential at the center due to this and due to this. Okay? For part B, when the switch is closed, then equilibrium is reached, determine the charge on the shell. Now there's an extra boundary condition, which is that the potential at the surface of the shell must be like E. What we need to understand is that the shielding effect will happen again. But this time, let's call the charge Q shell. This time when you put the negative Q1, there will be again, when you put Q1 inside, there will again be negative Q1 on the inner surface. So there'll be outer surface charge, which is equals to Q times the shell, Q of the shell minus Q1, right? Minus negative Q1. Because these two added up, the outer plus inner surface must be equal to the total charge on the shell. And then the second condition we can use is that the potential at the surface must be E. So if you have the other charge at Q2 at a distance 2r, then the sum of all these potentials must be equals to E, right? Note that Q1 and negative Q1, they don't create any potential difference between any point from infinity and the sphere. The reason is because the field is zero due to these two only. So if only Q1 and negative Q1 on the inner surface existed, then there will be no field everywhere else. The field in this whole region outside is zero. And potential difference is E dot dl. So it means that there's no potential difference from infinity to the surface of the sphere, which further implies that the potential is zero if only Q1 and negative Q1 were there. Does that make sense? If that is acceptable, then the next thing we can do is we can say that um, the potential due to the outer surface of charge, due to outer charge. Wait, hang on. Can I explain one that? Oh, yeah. So um, the shielding effect causes negative Q1 to appear on the inside. Agree? Like negative Q1 to appear on the inner surface, and then there'll be charge on the outer surface also, which is the total charge minus the inner charge. Okay. What I was trying to say is that due to Q1 and negative Q1, so only due to the charge in the shell and the charge on the inner surface of the shell, the potential is zero at the surface if we are only considering these two. The reason is because, as we described previously, if we are considering just these two contributions, the field outside is zero. Okay, E equals zero outside in this whole region outside. So if we are taking potential from infinity, where potential is zero, and we integrate along a path to the surface of the shell, and E is zero everywhere, it means that the potential of the shell must be E also. It must be V equals zero also, right? Because there's no electric field. If we are just considering Q1 and negative Q1, I mean. Do you agree? Okay. Um, then the next thing is the potential from the external charge will be like KQ2 over R, right? Wait, sorry. Oh, right, right, right. Wait, there's an extra step here, which is that technically speaking, we can't immediately find the potential on the surface because there is outer charge, right? And then in traditional electromagnetism, when you get infinitely close to the charge, then the potential is like not very defined because R approaches zero, then your function approaches infinity. So the what we actually do is we need to calculate the potential at the center first. Okay? Um, KQ2 over 2R. So this is the potential at the center due to this charge only. Okay? And then we need to add an extra component, which is that uh oh right, you also have the outer surface charge, which is KQ outer. So KQ shell plus Q1 over R. So this is the potential at the center, okay? V at the center. Now, I want to justify why the potential at the center is the same as the potential, like, is the same as the potential on the surface. So this might seem counterintuitive, but the explanation is actually quite simple. So, if you guys recall just now about the electrostatic shielding thing, we talked about how the external charge distribution would like arrange itself such that the potential is zero. Sorry, the field is zero inside the cavity, which basically just means that if we are considering the outer surface charge and Q2, then it will result in no electric field within this region, right? I don't get why. Um, Why is Q outer not just Q1? Oh, because like in this case, right, it's not neutral anymore. Like you connected the switch, correct? So like extra charge can flow in. It doesn't have to be zero or like net zero. Yeah, and then why didn't we take into account Q1 when calculating potential center? No, so what we're doing is we're trying to do like two things simultaneously. Okay, yeah. I think I didn't explain it very clearly. Basically, let's imagine we temporarily erased Q1 and Q and negative Q1. Then the potential at the center is this. Correct? Do you agree with that? If we temporarily erase Q1 and negative Q1. Okay? So now the potential at the center due to these two charges is just this. Notice that the potential at the shell is if we go from the center and we integrate along a line EDL, right? Like we integrate the electric field. But the point is the electric field is zero in the shell due to electrostatic shielding. The outer surface charge will distribute itself in a manner that will cancel out the electric field inside, which is exactly what we were talking about just now. Let me scroll up. Like this thing, right? The field inside must be zero. So if the field inside is zero, it means that the electric potential difference between the center and the shell is also zero due to Q2 and the outer surface charge. Do you agree? So V shell is also equals to this. If it was just Q outer and Q2. Do you agree? Okay, so the way we calculate potential difference between 2 points is we integrate the electric field, correct? E dl. But we proven earlier that for a conductor, the combination of outer surface and Q2 will cancel each other out such that the field inside will be zero. This is necessary to satisfy the boundary condition, which is that your conductor must be equipotential, right? It's the discussion we had about why when lightning strikes, you won't be affected if you hide inside a conductor. Okay, great. So if that is okay, then the next step is, since the field is zero due to outer shell and Q2, then the potential difference between center and outer shell must be zero also, because you integrate along a path to the shell where the field is all zero, right? So the potential difference has to be zero too. So in conclusion, V shell due to Q outer and Q2 is this expression. It's just VC. Okay? Do you understand? Are you okay with this part? Okay, great. Yeah, yeah. We'll get to it right now. So, fine. V shell due to Q outer and Q2 is VC. Now, we put back in, because superposition, right? We put back in Q1 and Q2. And we can erase Q outer and Q2 now because we have already factored in the two of them. These two produce V shell equals zero, right? Because, like what I said just now, when you do the electrostatic shielding thing, E equals zero everywhere outside. due to Q1 and negative Q1. So when you start from infinity and you integrate along a path to the surface, E equals 0 all the time. So the potential is 0 due to Q1 and negative Q1. So the total V shell is basically Vc plus 0. So this is like the contribution of Q1 and negative Q1. This is the contribution of Q outer and um, Q outer and Q2. Does that make sense? So there's four types of charge, but Q1 and negative Q1 collectively produce zero potential difference at the shell. Okay? Yeah, so this question, once you get the idea of conductors and what they're all about, the working is actually very short. It's just the hard part is trying to understand what is going on and what properties to use. Okay? So to not confuse yourself, I would recommend you just familiarize yourself and remember two properties of electrostatic shielding. Firstly, when you have any charge within the cavity, doesn't matter if your cavity is like a weird shape, if you put Q1 over here, there'll be negative Q1, okay? And negative Q1, this configuration produces E equals 0 outside, okay? This is always true. And then there is the other case, which is that if you put a charge Q2 outside, then there will be some charge, does not have to be negative Q2, okay? Does not have to be. There'll be some charge, and then this configuration produces zero field inside. Okay, so two things. Zero field outside if there's a charge inside, zero field inside if there's a charge outside. Okay? Does these two concepts make sense? Okay, yeah, so that is like electrostatic shielding in a nutshell. Those two things are most important, and then you can do this problem now. It just needs a bit of thinking. Okay? Yeah, it's a bit confusing now. That's why we put it at the end. Uh, I mean, I couldn't do it also. So, okay, last one, 2.15. So this question is very nice. It is very, very nice, but it's a bit tedious. So, the idea is that we can use Gauss's law because this is precisely the scenario I mentioned just now, where we know the electric field along the line, and we want to find the field along a direction perpendicular to the line. So this is like very good for Gauss's law. So we start by first calculating the field along this line. If we just consider one disk first, then the field is equals to integrating the like ring elements. Do you guys need me to run through that? Or okay, I'll just run through it now. The integral looks something like this: 0 to r k sigma. So this basically just does the concentric rings thingy. So this is your dA, then this is your length, and this is the factor that allows you to account only for this component. Okay? So when you evaluate this integral, you can solve this using U substitution. You should get negative sigma. Oh, there's negative here because it's negative charge. It's like this lah, basically. Okay, you can go try the integral itself. Shouldn't be too hard. And then the tricky part is like applying Gauss' law. So the way we do it is at the original center, we now draw a Gaussian cylinder. that looks like this. So the cylinder magnified has a distance r and a length delta z, where both r and delta z are very small. Um, we can calculate the field through the faces of our cylinder by using the result of this part. So like basically you'll have flux going out here and flux going in here. So I'm going to call this EZ and I'll call this EX. Okay? The net flux has to be zero because there is no charge enclosed. So Q enclosed 0 means that the net flux must be also 0. The flux through the faces, so this is delta Z, this is R. Wait, sorry, this is delta X, this is Z. Okay, so I won't use this one. To determine what the field E of X is, I can simply take 2 times 2 delta X dE dx dx. Okay, so let me explain what each term means. dE dx evaluated at x equals d over 2. This is because at the equilibrium point, E is 0. Okay? Because you have plates on both ends. So E equals 0 at the equilibrium point. Over here, E is 0. If you want to go out by a bit, then one of them will add on, the field strength of one will become stronger, the other one will become weaker by a bit. A bit is this thing, dE dx times delta x. This is the a bit. Okay, because if you have a function E, for example, against R, just generally speaking, then a small change, you can write it as dE is dE dr times dr, correct? So a small change lah, basically. So the electric field strength due to 1 at the center might be E naught, but then when they go a bit to the right, then it becomes E naught plus delta E. So over here it becomes E naught plus delta E. And then for the other one, it became E naught minus delta E. Okay, then when you add these two together, when you add these two together, the net effect is that you'll get 2 delta E. Correct? So that's where that's where this factor of 2 comes in. The second factor of 2 comes in because there are two faces. So the flux exits from both the left and the right face. Does that make sense? Do you guys understand where this comes from for E of X? Okay, so let me explain more clearly. So your cylinder looks like this right now. The electric field due to the first plate, so the first plate is over here, second plate is over here. The electric field due to E1 is like this. This is E1. Okay? And then due to the second one, there's an equal and opposite E1. So the net effect is that the field at the center at the equilibrium is 0. But right now we're trying to evaluate the field at one of the faces. So if we go to one of the faces, right, the left one will become E1 minus delta E because the field strength became slightly weaker because you went further from the plate. And then the right one will become E1 plus delta E because you went slightly closer, right? So the net effect is you get 2 delta E to the right. Okay? And then to determine what delta E is, or like dE lah, I'll just say dE, it is equals to dE dx evaluated at x equals d over 2 times delta x, right? Okay? Why do we have to do this when charge moving up? Okay, because right now we are trying to find electric field through these two parts, right? But we don't know that. What we do know is we know electric field along these two parts. So we can use Gauss' law to relate them. Does that make sense? Okay. So then we can determine what E of x is. E of x is just 2 times dE times pi z squared, which is the area of the face. Wait, sorry, the flux of x. Flux. Okay, this is the flux, but then you need to multiply by another factor of 2 because this factor of 2 accounts for the fact that there are two faces. This factor of 2 accounts for the fact that there are two plates. So the decrease in one will be coupled with an increase in the other. Okay, so there's a total factor of 4 for the flux. And this is the flux through the faces. This must be equal to the flux through, so if I call this flux of x, this must be equal to the flux of z. Flux of z is very simply just E of z multiplied by 4 pi z delta z, delta x, sorry, because you are looking for the curved surface area. So the height is 2 delta x, and then the circumference is 2 pi z. Okay, so from here we can determine, so we equate the flux to determine phi z is equals to, Ez is equals to negative z dex dx evaluated at x equals d over 2. Can? So the negative sign is because technically speaking, the flux is coming into the plane. So up to this point, are you okay? Flux of, oh, because z is like, by symmetry, it's going to be radially outwards, right? It's going to be like here, 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 correct? So we just want to find a curved surface area. The curved surface area of a cylinder is like simply just, wait, why is my mouse not working? The curved surface area is just 2 pi times the circumference times the height. So 2 delta x. Okay? So that's where the 4 pi z comes in. So we use just z. Okay, then we take EZ times that. EZ is what we're trying to find at the end of the day, right? That's the perpendicular line field. Oh, it's negative because it's coming in. The other flux is leaving, right? Because the total flux must be zero. Yeah, great. So now it's just math lah. You need to do a derivative on your function where we already determined what this is your E of z. Okay, so I'll write this as E of z. Wait, sorry, E of x. Okay, so we just need to perform this derivative as a function of x. So this is just okay. I won't do the derivative now. I'll just tell you guys what the answer is. But you should get like uh, let me see, what should you get? Oh, EZ should be negative z over 2 sigma r squared over, yeah, should be like that. Okay, and then you see that the force is simply just q times of this. So you multiply q times this thing to get the force. And then there is a proportionality to the displacement in terms of z. So this is just simple harmonic motion, right? Because the spring constant is like the constant in front. So then the period is just 2 pi square root m over k, where k is our spring constant. So all this stuff in front is like the spring constant. Okay, so I won't do the math anymore, but the idea is that your force turns out to be linear, and you can take the proportionality to be your spring constant. Can? Do you have any questions? In this diagram, oh sorry, I didn't see this. Where did the positive charge Q go? Oh, basically, right, we're just assuming that without the positive charge Q, what is happening? Like what the flux is. Because the force on the charge Q is due to the plates only, right? Like it's not due to itself. It cannot generate a force on itself. So there's no Q. We're just finding out what the field is when the Q is not there. Then you put the Q in, the Q will experience some force because there is some field, right? Um, does that make sense? Like we're just trying to find the field in that region first, and then like you put the charge in, the charge will feel a force. Huh? No, like the test charge cannot exert a force on itself, what? Right? We're just trying to find what the field due to the plates are. It doesn't matter what the field due to the charge itself is. Like our Gauss law thing is just trying to find the field of the plates. Because when you add, like I understand what you mean, when you add the charge in, the flux will change. But then, like we're not trying to find that. It doesn't really, like you cannot exert a force on yourself, what? So you only really care about the. Yeah, it doesn't. It doesn't. But assuming it's a static charge, like it's not a conducting plate now. It's just a fixed plate with a fixed amount of charge. Yeah, can? Great. Uh, yeah, okay, so that's all for these problems. You guys can try these. 3.1 is cool. There's quite a cool idea, but I think it's more high, it's like more hard lah. So 3.2, I do not think is worth doing. It's quite like nobody will ever think of it lah. 3.3 is also quite nice, but it has simplifying assumptions. So you guys can try it. Anyways, the questions here are definitely harder than SPhO nowadays. Like the type of stuff you can expect is like 2.3. This kind of stuff could definitely come out for SPhO, like nowadays. Like other than that, it's all not that easy, bro. So yeah. Okay. Do you guys have any other questions? Okay, if don't have, then yeah, we're done now. See you guys next week.